Hey guys, eMachine03 here. Welcome back to a brand new video. This video is actually going to be a little different from some of the other videos I've done on my channel in the past, and the reason is it involves math. Yeah, but don't worry, it's not just math, because it's not just a math problem. It's a math problem that was from an anime. Specifically, the third episode of the show Nichijou. Excuse my pronunciation. Now, in this episode, you see the problem during the scene where Yuko is in math class and the teacher puts up a problem on the board that we're going to be solving in this video, obviously. And the point of the bit is that nobody really knows how to do it. Either they don't know how to do it or they're afraid to answer because they're afraid of the teacher because when they get problems wrong, he beats them. Which is kind of messed up, honestly. I would hate to go to school there. But anyway, so they aren't raising their hands, and then the teacher alludes to like their student reports or whatever, and then they all raise their hands so that like even if they don't know how to do the problems, they still want to raise their hands so that they can like prove that they're being attentive and paying attention in their classes and stuff. So yeah, it's a strange series of circumstances and events. And as you'll see in this video, the students' fears of actually answering the question might be somewhat understandable because this is a pretty weird question, honestly. I'm not going to pretend that I am like a genius and I solve this. I'm like, those anime characters are stupid. I can solve this instantly. No, that is not what happened at all. In fact, when I saw this, when I was watching the anime, I was like, I could probably solve that. And then I analyzed it, and I was like, oh, there's no freaking way I can solve that. And I only really figured out how to solve this because of a Reddit thread where a few people were trying to solve this same problem, actually. I combined what a few people did in like different responses, so there wasn't like any one response I took from. But I sort of like combined their methods and used it to make one that both like I felt was clear and I also understood myself. Hopefully you'll be able to understand this method. I'll do my best to explain. So I'm not going to show you a like clip or screenshot of the show. I would like to, but the issue is I don't want to get like copyright striked or anything like that. So you can watch the show yourself. It's on Funimation if you want to go watch it. So anyway, let's get on to the problem. A quadrilateral ABCD is inscribed in a circle. Side AB has a length of 5 units. Side BC has a length of 4 units. And side CD has a length of 4 units as well. And angle B has a angle length of 60 degrees. Find the area of ABCD. Now, reading this problem, it seems confusing, but that's because this problem relies on properties exclusive to a quadrilateral inscribed in a circle. That a quadrilateral inscribed in a circle is known as a cyclical quadrilateral, as you can see on this Wikipedia article that I was actually using. And here's the area of a cyclical quadrilateral. And we're going to be using this in the problem. So if we want to find, if we go back to paint, we can see the goal is to find the area of this quadrilateral inscribed in a circle. And since a quadrilateral inscribed in a circle is a cyclical quadrilateral, then we're going to be using this formula at the end of the problem. And the reason I want to think of that is like you can't just solve it. You have to know what you're trying to do when you solve the problem. And what we're trying to do when we solve this problem is get to this. And you can see in order to use this formula, which is known as Brahmagupta's formula, sorry for the pronunciation once again. I guess I'm just speedrunning, trying to see how many cultures I can offend in this video. But anyway, we're going to need to know the lengths of all 4 sides of the cyclic quadrilateral. And then we will be able to find the area, and we'll be able to solve this problem and show once and for all that Yuko is a big fat dum-dum. But would you look at that? We only have 3 of the sides. This might be weird to visualize, and just generally this thing is going to be weird to visualize if there isn't a drawing. So that's why we're going to draw it. Generally with like geometry problems and stuff like this, but also like physics problems and stuff. It's just good practice to make a drawing that'll help you visualize it, and you can like better think of it. I do that often in like my classes. Like I had physics 1 just this last school year, and I definitely did draw a lot of diagrams. As you can see, I didn't really draw them that well, but it's not art class, it's math. Or in my case, it was physics. So, this is what inscription means. Or inscribed, or however. I don't even know if inscription's a word. That's like conscription. That's what's going to happen to me in a few months. But anyway, that might have been too dark. But anyway, cyclic quadrilaterals. So, a quadrilateral ABCD, that's referring to the vertices of this quadrilateral. Now, this is not accurate. The angles of this quadrilateral are in no way going to be 90 degrees. This is not a square. It's a quadrilateral. But for demonstration purposes, we're just going to write it like that because I'm lazy and I don't really know how to draw stuff. But anyway, we've got ABCD, that's the vertices, and that's what it's describing. And we can use these vertices to figure out where the side lengths are going to be. Side length AB, which is 5, would be here. BC would be here, and it's 4. CD would also be 4. And we know the angle at the vertex B is going to be 60 degrees. But if we go back to Brahmagupta's formula, as I previously described, we can't use it because we don't know the 4th side length. So we have to figure out what the 4th side length is. But first, we're going to use some special property, and probably one of the most important properties of cyclic quadrilaterals, and that is the fact that opposite angles are supplementary, which means they add up to 180. This is going to be useful later in the problem. It's not really super useful right now, but it's going to be useful later. So supplemental means the angles add up to 180. B and D would be opposite angles, obviously. So we can just algebraically represent this as B plus D equals 180. And then substitute in B, and give us 60 degrees plus D equals 180 degrees. And then subtract, and that gives us that D is equal to 120 degrees. And we can write a little angle symbol. It makes it look nice. 120 degrees. This is going to be useful when we're trying to find the length of side DA, because that's what we need. We need to find the last side so that we can figure out the area. In these sorts of problems, I think it's a good idea to make it more simple, and we can make it more simple and also more easy to work with by turning it into 2 triangles. And we can just turn the 2 triangles by drawing a line from A to C. Except that's not going to end up being a line, it'll be like a squiggle or something. So instead, that's good enough. So you can see here, that drawing isn't really that good. So, shoot. Okay, now we've got 2 triangles because we drew this line from A to C. The first triangle, we know 2 sides, 5 and 4, and we know the angle in between, 60 degrees. In the second triangle, we have 1 angle and 1 side, 120 degrees and 4. What's significant about the first triangle, triangle ABC, is that we know 3 parts of it. We know 2 sides, 5 and 4, and we know the angle in between 60 degrees. And if you know trigonometry, you know this means we can use the law of cosines to figure out what this side is, the side we just drew. We can figure out the length of it. And then that will allow us to find the length of side DA, which, if you remember, we need to know in order to find the area of this quadrilateral. We will now use the law of cosines so that we can solve this problem by First, figuring out the length of this diagonal. I don't know if it's actually a diagonal. I just saw the term diagonal somewhere one time, so I just use it. But I don't actually know geometry that well. Just enough to pass my standardized test in 9th grade, of course. So, but anyway, law of cosines. If you don't remember, the law of cosines formula states that c squared, which is like this side, equals a squared plus b squared, which are the two other sides, 5 and 4, minus 2 times a. Oh, why did I write it like that? It would be easier to just do 2ab cosine of c. C, it's uppercase C because a, b are still the two sides, but c is the angle that's opposite of this side. And we know these two sides and the angle opposites, so that allows us to find the length of this side using the law of cosines. There's some like fancy proof for this or whatever. I'm not going to go through that. I'm not a math teacher, and I think I forgot the proof as well. But we're just going to assume this is true. You can look it up if you're into that. So we'll just plug in these values. This is actually going to be pretty simple. We're not going to have to do like any algebra at all, and you'll see why. Just plug it in. Minus 2 times 5 times 4 times the cosine of the angle in between, which is 60 degrees. Well, actually, it wouldn't be the angle between. It would be the angle opposite the side. But I digress. So this looks like a mess because it kind of is. But it's actually not, because you can just type into your calculator and get a number. It'll be easier or harder to type in your calculator based on what type it is. But I'm going to use my TI-84 plus C. You could use like a Windows calculator, but it's kind of dumb. So just use like an actual calculator. 5 squared. Just type in 5 squared plus 4 squared minus 2 times 5 times 4 times cosine of 60. And don't forget to have it in degree mode. And you'll get 21. That's kind of surprising. You might have expected it to be like some weird irrational number because of the cosine. But one of the identities that you learn in trigonometry is that the cosine of 60 is 1/2. So that makes it better numbers to work with. But we're not done. This is squared. You got to square root both sides to get the actual answer. C is going to equal square root of 21. And this C, if you want a decimal approximation, we're not going to really need this, but if you want it anyway, it's going to be approximately to 3 decimal places. Remember, this is not the exact value. 4.583. So we'll put the like actual exact value there because it looks nice, in my opinion. I mean, none of this really looks nice, but it'll be easier to work with, and you'll see why once we get to the next step. So now we need to figure out the length of side DA, and we can do that because now we'll be able to solve this triangle ADC because we know the angle, the side, and 2 sides. We will just use the law of cosines and plug in the values where they belong. Remember, the opposite of the angle is going to go in the c squared spot, but square root of 21 squared, that's going to end up being 21, but I just wanted to write it out because it makes it easier to understand. And so we know one of the other sides, it's 4, but we don't know the other side. That's DA, but we're going to write it as D because I did a test run and I wrote it as DA, and it's annoying, so I'm going to write it as D instead. And then we'll do 2 times, sorry about that, 2 times 4, oh, I hate tablets. 2, I wish I had like a whiteboard or something, but then I had to like do a face reveal. D, and then cosine of opposite angle, which we know is 120 degrees. And now we can actually solve this. This might not seem like something you can solve at first glance, but since it's just one variable we don't know, we can solve it. And so we'll just make it a little more simple by doing some basic math. I don't know if it's basic, but it's probably basic math. I don't know. But anyway, so square root of 21 squared, that's just 21. Cancel out, Think about it. It would make sense. 21 equals 16, because 4 squared is 16, plus d squared minus 8, because 2 times 4 is 8, times d times cosine of 120. I'm going to do that in its own step. Remember how I was talking about how like one of the math things you just know is the value of cosine of 60? It's going to be the same thing for cosine of 120. This is sort of like a trigonometry concept. So if you don't really know this already, you've probably gotten lost by this point. If you haven't, you've got a bright future ahead. But anyway, so we know cosine is 60, and then that's a representation of how angles work. Standard position with the angle starting on the positive x-axis and rotating counterclockwise if it's positive. So this would be 60 degrees, and this would be 120 degrees. But for 120 degrees, in order to find the trigonometric ratios of 120 degrees, we need to find the reference angle, which is going to be, like, this whole thing is 180 because it's half of 360, and the full rotation is 360. So anyway, half of 360 degrees would be 180 degrees, and so if half of 360 would be 180, and then if you subtract this angle would be 120, as you can see. And if you subtract that, the reference angle would be 60 degrees. So if you take the cosine of the reference angle, it would be 1/2, because the cosine of 60 is 1/2, as previously discussed. But the difference here is that it's in the second quadrant, and cosine is negative in the second quadrant, so the result would have to be negative. So if we just write this out again, we can do like 21 minus 16, just make it work a little easy, less steps, less work to do, d squared times negative 8d times cosine of 120, cosine of 60 is 1/2, but it's in the second quadrant, so it'd be times negative 1/2. And then 21 minus 16, it's 5, because 5 plus 16, 21. Just check it out every now and then, Might mess up your mental math. It would be especially kind of embarrassing to mess up mental math if you're recording a YouTube video. And so here, negative 8 times negative 1/2, negatives cancel out, 8 times 1/2, 8 divided by 2 is 4, so it's just d squared, wait, that's, did something wrong? Yeah, 16 plus d squared. Yeah, plus negative 8d, but then you just cancels, so then it just becomes plus 4d. D squared plus negative 8, that becomes d squared plus 4d. And then you want to turn this into a quadratic so that you can work with it. So we'll just subtract 5 from both sides, and then now it's a quadratic d squared plus 4d. Impressive. And d minus 5 equals 0. And since it's equal to 0, that means we can just factor it and use the zero product property. Yeah. We can just set it equal to 0, and then we need to, in order to like factor this, there's many different ways you could factor it. I'm going to use my way though. What you need to do, you need to find two numbers that add up to 4 and multiply it to negative 5, and then make those coefficient of 2d terms that you'll be replacing 4d with. And that would be 5 and negative 1. And you just write it like this because it's easier. D squared minus d plus 5d minus 5. And the reason I did that is so that you can factor it, because the next thing you do is you factor out the common factors, and then factor out a d minus 1 from both. And now use the zero product property to assume that either d minus 1 evaluates to 0 d plus 5 evaluates to 0, or both of them evaluate to 0, because when you multiply something by 0, it just becomes 0. You could say d minus 1 equals 0, d plus 5 equals 0, d equals 1, or d equals negative 5. But for our purposes, length cannot be negative, so d is just 1. And would you look at that? After all that work, we've got the number 1. Sometimes that's just how math works. You do a ton of work to get a really simple number. But that's usually actually a good thing, because when you get a simple number, that means you haven't screwed it up somewhere. There are a lot of places to screw up in this mess of work, I'll tell you. But now, we can go back to the Wikipedia article and see. Would you look at that? We've got all sides of this. We have all the sides of this quadrilateral. A, B, C, and D. So we can use Brahmagupta's formula. But first, we have to find the semi-perimeter S, which is A plus B plus C plus D, all divided by 2. So we can just do that right now. It's actually pretty simple. I'll just draw an arrow to make my work a little easier to read. Semi-perimeter equals 5 plus 4 plus 4 plus 1 all over 2. S, and then you can just do it pretty easy. 5 plus 4 is 9, plus 4 is 13, plus 1 is 14, 5 by 2 is 7. So S is 7. There you go. And then now you can use Brahmagupta's formula, because this is a cyclic quadrilateral. You can use Brahmagupta's formula to find the area. Just in case you don't remember, I'm not going to copy the formula again because it's kind of long, but I will go to the Wikipedia article, show it to you. It's right here. Oh, this is an image, I guess. Yeah, so I can't really show it to you, but I can circle it with my mouse. The area, I don't know why we're using K to represent it, but why not? The area is equal to the square root of the semi-perimeter minus A times the semi-perimeter minus B times the semi-perimeter minus C times the semi-perimeter minus D. And then that is equal to the area. So we are almost done, surprisingly. It's probably feels like it's been a while, and that's because it likely has been a while. But we are almost done. So just one more thing to do. 7 minus the first side, 5, times, 7 minus the second side, 4, times 7 minus the third side, 4, times 7 minus the first side, 1. And then we can just simplify that. 7 minus 5 is 2, times 7 minus 4 is 3, times 7 minus 4 is 3, times 7 minus 1, which is 6. And now we can find 2 times 3 times 3 times 6. That's 2 times 3 is 6, times 3 is 18, times 6 is... Wait, I think it's 108. Let me check though. 3 times 3 times 6. Yep, that's 108. Oh, that is kind of long. And there we go. That is the exact answer for this problem. But that's not really that human understandable, so we'll make a decimal approximation as well. And if we approximate it to 3 decimal points, it is going to be 10.392, right? Yeah. Units. The reason I wrote that units squared thing is because area is squared. So if this was like centimeters, it would be centimeters squared. But since there's no units, we just say units is squared. And that's it. We have solved this problem. Oh, what the... okay, it's good now. We have solved this problem Look at that. We have found the solution to this problem. That's crazy. That is pretty cool. And if you've learned anything from that, from this, it's that, yeah, there probably was a reason those students were struggling to figure out this problem. It's not a very simple solution, I will admit. But that's going to do it for this video. Thank you for watching, and I hope you had a good time. If you'd like to see me do more videos like this in the future, please let me know in the comments down below. And if you have any suggestions, I would like to see those also. And if while watching this you have any of your own methods that you might use to solve this, I'd like to see those also. Yeah, this is actually a pretty interesting problem. I won't lie, but that's gonna do it. As always, I will see you guys later.